All right, very important. Very first thing. Does everybody have Inventor Pro running? Everybody has an account. Haven't gotten any questions about accounts being set up or how to verify, so I'm assuming everybody has an account. Does everybody have a PC that they can run it on, or they've configured their MacBook in a way that they can run on it there? If not, right, you have the option of using the computers in the lab in the manufacturing space, but you will have to be there to take classes then, right? Usually you can't take class from home because during class you'll have to be able to access the software. Right? It's very important. So either way, make sure you have something. If you have questions, if you're not sure how to set something up or something, just let me know, and I'm happy to help there. Any questions about Inventor? Apparently not. Then let's get going. Today we're going to be talking about threads and fasteners, and that's the last topic that we'll have before we jump into Inventor. And so threads and fasteners, I think we're all aware of what they are, right? I think in most houses you will find a little jar somewhere or a cupboard space or something that is full of some kind of little screws and nuts and bolts that got not used for something, and nobody wants to throw them out because we could probably use it for something else. So there tends to be a lot of these around, right? So what we talk about fasteners mainly, or the first thing that we usually think about, is that we're trying to connect two pieces together, right? We'll have maybe a big piece that has the thread in it, and then we have a screw that goes into it to connect another piece together, right? Or maybe it's just two pieces that get connected. So that's what we need. That's what we use for connecting parts. We also use it for adjustments, right? So here's a little tool, and basically that angle is being adjusted by opening and closing this or turning this the screw on the back here. Does anybody play piano by any chance in this group?
Yes.
Yes. So you are very aware of another piece of furniture where we tend to use this kind of an adjustment, I'm guessing.
Dale, Tommy.
You have a chair that you kind of turn to get it higher or lower. At least that's often the case when you have a piano, right? So that's the same idea here, right? So you're basically using this thread to have the chair rise up or rise down depending on how tall you are. I used to play piano when I was younger. Even when I was younger, I was relatively tall, so it was always a big fun. First thing I have to do whenever I sit down at any piano was adjust the chair all the way down so it fits to me. Right, so it's adjustments. Another thing that we do use them for is for power transfer. So I hope you've all at least practiced changing a tire once in your life, because you never know when you'll need it, and when you'll need it will be the last or be the worst opportunity to try it out, right? Is we change a tire. We usually have this little, like something that looks similar to this, might have like a different shape or something, but this is to lift the car up, right? So you can take the tire off the car, call it car jack. And that the way that it works is basically we're using one of these rods here to connect here to turn, and it's using that turning motion into a lifting motion. It does that by this thread right here. And then if you're doing any kind of arts and crafts work, any kind of shop work, right, then you have a mace like this, where you can kind of pull these things together to hold something very, very tight as you're working on it, right? If you're doing woodworking, or if you do jewelry or any of those kind of things, right, then you'll come into those kind of things, right? So that's what we use threads for. Seems I'm losing cameras instead of gaining them. Everybody here should have their camera on, not off. All right, so that's generally what they look like. If we want to be very specific, right, then we can say we have two general types. We have the external threads, like the screw that we have here, right? Basically, we have some kind of a cylinder and the thread looks as if it's on the outside. Or we could have it the other way around, where we have it on the inside. Right? So kind of these nuts are our standard type that we see, right? So we can have internal and external threads. Now, how do we create internal threads? Well, we basically have what we call a tap drill, right? That'll be this, and we kind of just like we would with a regular drill, we drill that into the metal, or usually it's metal, right? We don't usually do it in wood, and we certainly usually don't do it in plastic because those don't hold very well. But you'll see one thing that's very specific about these drills is that they don't go all the way around, right? They have these kind of big carve outs, like here, this one, these one have multiple ones. What do you think those big carve outs are for? Drilling. Yeah.
So when you have something that's like, like whole, like complete with material, when you go through, like you have, like, I know the material will come out at the end, but you also need something so it doesn't like break the la broca. I don't know how I say it in English. The drill thing.
The drill bit. Yeah,
yes.
That's exactly right. So like in the drills that we use to drill holes into the wall or something like that, right? There's a very clear path for the material that you're drilling out to be pushed out, right? So if you drill, you always see that the stuff is kind of coming at you, right? The same thing here, and that's what these big open spaces are for, right? So there's not enough space, of course, for it to move along that thread all the way out, because there's not going to be any space. So we have to have these center parts. Plus, we're drilling usually into metal, and so that's especially difficult to get out. But so for every standard kind of thread that we have, and we'll talk about all those standards in a little bit, we'll have a different type of tap drill that we can use to drill what we want to have. And here's just another cutout of it, right? So basically, that's this is what we call the flute, right? That's where it's coming out, and then the very tip of it is, especially for the bigger ones, is not going to go out to a sharp tip, but kind of goes to a blunt tip, because we don't have to drill all the way in to make it to be usable. So that was the internal threads. I'm sorry, internal. Now for the external threads, we have what we call a die stock. So basically, we take whatever our cylinder is, we put this fit this on the top of the cylinder, so it kind of fits up like this, and then it gets turned around, and as it goes around, it just scrapes off the metal to create the thread, right? And similar to what we had with the drill, we have to have these open spaces so that when we carve out the metal, it has enough space to fall away, because of course we don't want that to get stuck, right? So it's a pretty simple way of creating these. Now let's get to some of the technical terms that we have. So we have the top of the thread, we call it crest. The bottom, we call the root. Kind of the slanted surfaces that we see, we call the sides. And then the difference between the crest and the root, we call the thread depth. And some more, and these are the more important ones. The outside diameter, so from crest to crest, we call the major diameter. From root to root, we call the minor diameter. And then halfway between, we have what we call the pitch diameter. Now, what is the pitch? Well, if you play soccer, then you know what the pitch is. That's the field that you play on, but of course, that's not what it is here. The pitch here is the distance between two consecutive threads, right? So if I'm standing on my little screw, if I were standing up here from a little ant, right, and I start walking along this crest, right? So I'm kind of walking all the way around. And once I come back up, I'll be on the next one, right? It's kind of hard to see, of course, because we always see the front, but we're kind of going down here, then we're coming back until we come back to the front, right? So this distance is what we call pitch. Pitch is, of course, then measured as a length, right? So it's millimeters or inches. We'll see that sometimes we do the pitch, and sometimes we do pitch per distance, right? So that will not have a unit. The axis is just kind of a symmetrical axis of our bolt or of our cylinder. And then the angle between these two sides is what we call the thread angle. And there's many different forms that we can have for these threads. Originally, the first ones that we kind of used, especially with metal parts, were what we call a sharp V. So it's really just up and down, up and down, up and down, 60-degree angle between them. But it turned out that these were not the best. Now, what are two things that would be potentially problematic with this shape, right? Imagine this is if you cut through the screw, right? That's what you would see, these kind of sharp peaks and sharp valleys. What could be an issue with those? Whenever you see something sharp, what's the first thing that you have to worry about?
It cuts.
Cut your fingers, right? If you have a metal screw that has like a sharp tip edge, risks are that you're going to cut your fingers, right? You don't want to cut your fingers every time you touch a screw, right? So that's already not very good. Now, I have to see through how many of you, a couple of you at least, have taken materials, I think, if I remember correctly. So for those who have taken materials, why would this down here also be an issue? And so in materials, for most of you, you haven't taken materials yet, but you will talk about, in materials, you'll talk about what we call failure, right? And so there's one place where you can get failure is at what we call cracks. So anything that has a sharp tip will focus stress at that tip, right? So if you look at this, if this thread were under load somewhere, and you would kind of look at what the stresses looks like, then you would find out that there's big stress concentration at this very tip. We also talked about this briefly in bio-inspired design, so there's no excuses for not knowing this, right? So whenever you have one of these sharp corners, you get a stress concentration. And of course, if you get a stress concentration, that's a place where you would expect failure to happen first. And so if you have these very sharp tips, that means it's likely that there are higher chances of getting failure there, right? So those are the two things why we don't like those sharp V's very much. So we came up with some other stuff. One of them is what we called the thread form is called unified. That's the one that is mainly used in the US. And you can see it basically gets rid of that problem by rounding off in a curve those tips, right? So this would be kind of the thinner one that you see would be kind of just a straight up V. But here it rounds them off. And there's very exact how deep and what the curvature is and all those kind of things, which is not that important. But it's nice and rounded off, so it means you're not going to be cutting your fingers, and of course you're not concentrating the stresses quite as much, because a round corner has a lot less stresses than a sharp one. That's the unified. And then we have another one that we call the metric one. And that is basically where we just flatten out what the tops and the bottoms are. Right? It's a little easier to produce than the unified one. But the idea is the same. And as you can see for all three of them, all three have the same angle between the sides, right? The pitch angle is the same. And then we have a third type, a general, or another type you could say, right? Where the shapes are more blocks, right? So this would be something where we have rectangles. Now, do you remember these rectangular threads from somewhere? Talked about them in a class, and I know that you've all taken them. Some of you just took it recently. What class did you guys take with me last?
Statics.
Statics. We talked about square threads. Yeah. Right, we talked about square threads in statics. Right. The reason why we stuck to square threads is because they're easy to do in statics. But they're actually also very useful when you think about anything where you want to transfer a lot of stress from one place to another, right? So again, when you think about that car jack, those are usually square threads, or if they're not square set threads, then they're these Acme threads that are like almost squares, right, or almost rectangles. Also, if you think about the thread that is under the chair for the piano, right, those are also going to be square threads, right? So that's where we see them, because we're trying to move a lot of power from one part to the other. But we're mainly going to be talking about the unified and the metric ones. Another difference that we have is left-handed and right-handed. Of course, the right-handed screws are the general ones that we use. Like most everything that we have is right hand, right? Righty tighty, lefty loosey, right? That's the idea. So whenever you have something that you want to open up, then remember that. Like, if it's not working easily, then you know that you do have to open it, loosen it, turning it left. All right. So that's very important. Now, we do use some left-handed threads every now and then. Does anybody can think of a reason why in some things we want to, or maybe knows an example where we use left-handed screws? What are basically going the opposite of what we usually have. I can think of at least two, and I think both of those things you've at least seen, probably used one of them. The other one may or may not, depending on how involved you are in your kitchen household. One is the crankshaft. I'm sorry?
No, I thought you were going to say the can opener, which they're usually for right-handed people. And
no, with the can, like all your, like, if you do jars or stuff, they will all open to the right. That doesn't.
Yeah, but I mean, like the devices.
The devices, okay.
Yeah, are usually for right-handed, but it's very rare to find some for left-handed.
But I'm not sure if the thread on there is going to be the opposite direction, because it's really on a can opener. There's not a thread, right? There's just two gears that work together to run a can opener.
Right.
I think. I mean, you might have some more elaborate can openers than I have. Could very well be. But one thing where we see this all the time is in the crankshaft of a bicycle, right? And not so much directly in the crankshaft, but in the places where we attach the pedals to kind of the crank arms. And the reason for that is that we want to make sure that for both of them, that as I'm pedaling, I'm not loosening, right? If I had the lefty loosey on both sides, then as I'm pedaling, I would loosen one of them all the time, and the pedal will keep on falling off, right? So that's why we have one that's the opposite direction. The other example, I don't have a picture here, but is if you've ever opened or closed the gas container on your grill or for your house, you will notice that also goes in the wrong direction. That's why they have the little arrows on top to make sure people know which way to go. Do you have any idea why that would be the case? In general, anything that is with gas, even the gas, valves, all work in the wrong direction. The simple reason is that we don't want people to open gas valves by accident, right? So basically, if there's a whole bunch of stuff and you're just opening stuff, right? So if you're trying to open it and it's gas, it will not open because it's going to be going the wrong direction. Because of gas is of course burnable, and we don't want to start fires if we're not intending to do them. So in general, a lot of things that where people don't want you to open it, or where people want to make sure that you know that you want to open it, they will be working in what we would consider the wrong direction. Another thing that we don't see all that much, but is sometimes we can have multiple threads at the same time, right? So in this case, this is not a single thread. This is 3 different threads. That's why they have 3 different colors. Of course, on a real screw or something, we wouldn't have the 3 different colors. Well, of course, just the background of the metal. But you can see that you have multiple threads if you just look kind of straight at the screw, and you'll notice that there's 3 different places where this thread starts or ends, right? Otherwise, it'd be just a single one if you just think about your standard screw. All right, so now we know generally what threads look like or what they are. And but this is a graphics course, right? So how do we represent them on a drawing? And there's basically three different ways of doing it. We can do a detailed representation, we can do a schematic representation, and then a simplified one. And of course, we all like the simplified version. But let's start with the detailed representation, right? If I just told you draw a screw, then you would do something like this, right? Now, if you want to do this by hand on a piece of paper, this is extremely painful to do. Well, it will take you forever to draw this little screw because you have to do all these have to be perfectly parallel and all that kind of stuff, right? So it's going to take you very long to do. Even if you do it on a computer, it takes you a long time. I can tell you, this is drawn. If you look closely enough, you can see that these are just lines that I stuck together, right? Even with copy and paste, like even just creating one of them and then copy and pasting the other ones still takes a lot of time, right? Even if you're an inventor and do copy and paste in there, which is easier because you can direct them and all that kind of stuff, still takes a lot of time, right? So it really, really takes a lot of time, and it has a lot of details on that are not necessarily usable, right? I don't really have to know exactly what this thread looks like in order to produce a part, right? But on the benefits, it really does look like a screw, right? I mean, if I look at this, and I'm kind of in the technical space, right, I will definitely see that this is a screw, but way too much work. That puts us to the schematic representation, which is of course a lot less work, as we can see, right? All we do is basically draw the cylinder, and then the area where we have the thread, we kind of have this simplified or this schematic version of it, right? Where we have the outside is going to be the major diameter, the shorter lines are going to be the minor diameter, and then the distance between these full lines is going to be the pitch, right? So that would be the simplified version of doing it. Now, this still, with some squinting, you can still think about this as a screw. It is a lot easier to draw than the first one, right? This is just a couple lines, so it's definitely faster. But while it is easier, it still takes a lot of effort, right? I mean, this screw only has 1, 2, 3, 4, 5 crests, right? So that's not very many, right? If you think about an actual fine screw, right, it will have 20 of those or something. So it's going to still be a lot of effort. And again, it has a lot of information there that we don't really have to see directly, right? And so that comes to our last option, which is the simplified representation, where we basically just draw the cylinder and then draw in as hidden lines where our minor diameter would be, right? So we're given the major and the minor diameter and nothing else. We don't say anything about the pitch. So this is relatively easy to draw. However, if you don't know that this is a screw, then you would never recognize it, right? So it's something that's really for people who are doing drawings. And of course, this does require more information, right? I have to tell it, for instance, what the pitch is, because I can't see it here. All right, now let's talk about the different thread types that we had, right? We said the main ones that we use are the unified threads. Those are the ones that were kind of rounded off at the top. And the other ones were the metric ones, but we'll start with the unified ones. These are the standard in the US, the UK, and Canada since the 1940s, so they've been around for a while. Costa Rica, you will find both unified and a unified national and metric. There are 3 main series that we use for unified threads. There's the unified national course. We use that for any day kind of things that we use around the house. We have unified national fine, UNF. This is something where we want to make sure that our screws stay nice and tight, right? So the thread is going to be closer together. And then we have extra fine, UNEF, and that's basically only we use that for the aeronautics industry or for screws that are very short, right? And these are like the difference between these 3, coarse, fine, and extra fine, is how close the threads are together, right? So when we say something is fine, it means that the threads are closer together, right? So they're harder to distinguish from each other. And so, of course, if you have a very short screw, you have to kind of squeeze them all together and able to still get enough to actually make a connection. We also have what we call thread classes. So we have the general tolerance one. Those are going to be screws and bolts that are relatively loose. They're going to be easy to tighten, easy to loosen, which is good if you're assembling and disassembling something relatively often. Then 2 is the normal one. That's pretty much all we're going to see is normal production ones. And then 3 would be high accuracy. And of course, just like with anything with tolerances, 1 is going to be cheapest, 2 more expensive, and 3 the most expensive. All right. In the previous slide, we said that we'll need extra information if we want to do this simplified drawing. And the extra information that we have is what we call a thread note. And this is what a full thread note would look like. Of course, usually it's not nice and colorful. I just did the colors for us to kind of be easier to understand what is what. The first part that we have is the major diameter, in this case in inches, 3/8. The next thing that we have is the threads per inch. So this is not the same as the pitch. It's basically 1 over the pitch, right? So how many threads do I have per inch? So the bigger this number is, the finer my pitch is going to be because I have more threads per inch. The next one, UNC, is the thread series, right? Again, this would be the coarse one. UNF would be the fine one. Then 2 is the thread class, right? Remember there was 3 classes. The one that's kind of cheap one, which is nice and loose. The second one, which is the normal one. Third one was the very high tightness ones. Then A and B stand for external and internal. Now, why on earth they didn't use E and I have no idea. Seems to me more logical to use something that fits to it. The way that I try to remember it is that if you over accentuate the A, you could say it's external. That's about as good as I can get, right? So A is for external, B is for internal. Most of the time we don't need it because we can, like on the drawing, see if it's external or internal. And then at the very end, we have RH for right-handed and LH for left-handed, right? What we'll see, oh, and the thread depth. Let's not forget, that's the thread depth, right? So a lot of time when you buy your screws, you'll want a certain thread depth, like how long that thread is in total, or the threaded area is. Now, for most cases, we will assume that it's the thread class 2, that it is, we can see if it's external or internal, and we'll assume that's right-handed. So in most cases, we leave off the last 2 parts, right? So the thread note would just be 3/8, 10 UNC, and often, like, we don't even care so much about the length of it. All right, so let's go through these. Let's see, do another short-term memory test here. What was the 1/2? What does that stand for?
The biggest circumference diameter. What? Yes.
The diameter, yes.
Uh-huh.
And what if we have 2 diameters, right?
Yeah, but that's the biggest one. Like
The
the
biggest, we call that the major diameter.
major, uh-huh.
So 0.5 inches. All right, so I'm not going to be super crazy about the leading zeros are not here because these are not really technical tables anyway. But if you want to be technical about it, as long as it's inches, it shouldn't have a 0 in front of it. All right, what was the 13? What does that stand for in our case? This one up here.
The depth
No, there's the depth where we have something written down here.
below that.
Given the depth. What is the other thing that is very important? So if we have the diameter, what else do we need to know?
The amount of rings per inch.
Exactly, right? So we call that threads per inch. Right, so we have, if you think about that cross section, right, we'll have 13 of those little crests, right, within a certain inch. Now, if we want to talk about pitch, right, that's the other way that we describe that. That will be just 1 divided by however many threads there are per inch, right? So my pitch would be 0.077 inches. All right, then UNC, what does that stand for?
The course, I don't know what the UN, but that was the course one.
United Nations course, not unified.
thinking.
Unified National. Any basketball fans here? No? UNC, University of North Carolina, usually pretty good basketball teams. Tar Heels. Right, so that was Unified National Course. Right. The main ones that we're going to use be Unified National Course and Unified National Fine. Extra fine, we're not gonna touch that much. All right, what did the 2 stand for?
It was the thread class.
Exactly, right? That was the thread class. In this case, 2 is normal production. That's what we have. Now, B, external or internal?
External.
External, exactly, right? No, B internal. B is internal, right? So B is internal, and then LH. What does LH stand for?
Left.
Left-handed. Or if you travel a lot, it's also Lufthansa. But that's a whole different. Left-handed. Right? So this would be how we understand all of these different parts in. Again, most cases, we're going to end after the thread series, right? Because we're going to assume it's the normal production class. We will assume that we can see from our drawing if it's internal or external, and we'll assume that it is right-handed. Right? So if it's not the case, right? If we're using 1 or 2, or it's right-handed, left-handed, then we would definitely want to put it. All right. So again, just like with our tolerances, we get another nice set of tables that we can use, right? And so in these tables, you will see that we have coarse, so UNC, we have fine, UNF, extra fine, UENF. We will have the basic major diameter given here. Then we'll have the threads per inch, THDS is threads. And then we have the tap drill diameter, right? So this would be the type of tool that we need to use if we want to create an internal thread. And you will see that the nominal size is given in inches. However, if there's a little number in front of it, that means that it's not inches. Those are just numbered, right? These are the very small ones, because it's kind of, the smallest other ones that we get is 1/4. So if you want to go down into these, right, these would be very, very strange numbers. So that's why they're given as 0 through 12, right? So it's careful to look at. And then you'll see once we get to of course, the real ones, right? So 1/4, we can see the basic diameter is 0.25 inches. And then for each of those, we can see if it's coarse. If we stick with a 1/4 one, right, we can say if it's coarse, it would be 20 threads per inches. If it's fine, 28, and if it's extra fine, it would be 32. All right, so that's how we would read this table. Another very important thing is on top, as you can see, and that is what we call, that's the equation that we get to approximate what the minor diameter is going to be. If you remember all the way back to when we looked at the slides, had all these different numbers on them for like how to thread depth and everything would look at the different, or would fit to the different thread types. So we can simplify all that by doing the simplified calculation here, where D is the basic diameter, which we're given here. P is the pitch. You have to be careful because the pitch is not equal to the threads per inches, right? You have to do 1 over this number. And then we have this crazy number here that we have to multiply by, but all that will give us lowercase d, right? So this is the equation that we're looking at, right? So lowercase d is the minor diameter. It's not in the table, but we can calculate it. Major diameter, this factor here, and then the pitch was just 1 over threads per inch. All right, let's try this out. Let's say we want to do the drawing of a number 4 coarse external, right? We can see that's external here, thread. First thing that we have to do, pull out our table, go in and look for number 4. That's what it is right here, right? So we'll know what the basic, what the major diameter is, and now we know like coarse and fine. We don't have ultra fine, extra fine in this case because it's too small for that. All right, so we are given coarse. So that means we need to grab this right here. So now we know that we have 40 threads per inches. So if we want to write that down, then we can say, well, we have a number 4, and then we have 40 threads per inches, and we know it is coarse. Course, that would be our thread node. Now, if we want to know what the minor diameters, then we can take our equation, go back to our table, our major diameter is given, so we can plug all those numbers in. Again, very important to remember that we're given in that table, we're given threads per inch, but in the equation we need pitch, right? So we have to divide it 1/40 to do all this. Now with that, we can figure out what our number is, right? In this case, 0.0849 inches would be the minor diameter. All right, with that, this is just a summary of it all, right? So we said our thread node was going to be 4-40 UNC. Our major diameter we looked up in the table. Our minor diameter we calculated, and we saw from our table that we have 40 threads per inches, which gives us a pitch of 0.025. Very good. So of course that should be inches. Missing a unit here. All right, but that's what a table like this would look like. Of course, always good to do a quick check, right? Your major diameter obviously has to be bigger than your minor diameter. So if you miscalculated, you will get a number here that's bigger than the other one. Definitely not correct. All right, any questions so far? So this was all unified national, right? This was all inches. And now we're going to swing over to the other thread type, and that's metrics. And the metric ones are very closely related to what we learned for metrics and tolerances, right? Those were all those H7s, K5s, and all that kind of stuff, right? So we'll do the same thing here. We'll have something that looks like 4G, 6G, something like that. The first of these numbers is always for the pitch diameter, right? That was the one that was halfway in between the crest and the root, major and minor. And the second one is either for the major diameter, if it's external, or the minor diameter, if it's internal. Now, why do we do major and minor differently for these two when we think about the tolerances? Think about the external one, right? If I look at my external, if I cut through it, right? If I wanted to measure something, how would I measure the minor diameter on a external thread? Be very difficult to do, right? Because I can't use a caliper to go from one bottom to the other bottom because they're going to be at an angle. So it's really impossible to get, and it would have to have a very fine caliper anyway to get into those, between those threads, right? So for an external one, it is impossible to get the minor diameter, so we have to use the major diameter, right? That's going to be easy to measure because that's just kind of crest to crest to crest, right? On the other hand, if I do the internal one, right, where I drill into it, I cannot measure the major one. I can only measure the minor one, right? That's why it's different here. All right, if we use uppercase letters, we're talking about internal. And if we use lowercase letters, we're talking about external, right? So in this case, this would have been an external, right? Because they're both lowercase. If these two are the same, right? So if this was 6G, 6G, then we can contract them together and just do it right at once. If there's nothing given, then we'll assume that for internal ones, we have a 6H, and for the external ones, we'll have a 6G. Now, the good thing about all of this is that we usually just assume that we have 6H and 6G, so we can happily forget all of this because we're usually not using those thread nodes. But if we want to, again, look at a full thread node for metric, then we'll get something that looks like this. Basically has very similar information in it, just looks a little different. The first one is M. And that just stands for metric, so that we know we're not looking at a unified national. I always thought that it stood for machine because those were mainly our machine screws, but it stands for metric. The next one is the major diameter given in millimeters, in this case 8. Then we're given the pitch, also in millimeters, right? So in this case, each crest is 1.25 millimeters from the next one. Then we're given the tolerance class. And at the end, right-handed or left-handed, plus the thread depth again. All right, so if we know all of those, we can understand what these are. Now, again, most of the times, we're gonna assume that we can see if it's internal, external. We're gonna assume it's right-handed. And unless we're given a very specific other class, then we'll assume that it's 6H or 6G, depending on if it's internal or external. So again, just like for the unified national ones, we can drop this whole thing. So we don't have to worry about those crazy tolerance classes. All right, let's see how we did this time with short-term memory. What does the M stand for? What type of threads are we looking at? Metric, right? It's a metric thread. M is for metric. What did the 12 stand for? And the first number.
Was the diameter.
Which one? Oh, we have two
The major.
The major one, exactly, right? So 12 millimeters. And you will notice that there's not a space between M and 12, right? So that those are written right together. Then what does the M's, the 1 stand for? It's the next number.
The pitch.
The pitch, right? So how far is one thread from the next? In this case, be 1 millimeters. Then what do we have next? What does the 4H stand for?
The pitch tolerance.
Very good. And the 6H? For the 6H, we have to think a little bit, right? We kind of first have to figure out, is it internal or external?
The major tolerance.
It would be the major tolerance because it was external, because all these are lowercase, right? If all these were uppercase, then this would be the minor tolerance because it would have been internal. Right, so that's kind of what we have to do. And then LH.
Left-handed.
There we go. Right, so those were all the things that we can see. And of course, just like for the other one, we have a nice little table here as well. In this table, we'll have the nominal sizes, right? So 1, 6, 1, 8, 2, those are all like the major diameters. And then we're given the pitch, right? And we're given that for coarse and for fine. Those are the only two we get. We're also given the tap drill. Again, that's what we would use to create these, the internal ones. And then we have a similar type of equation, like the numbers are a little bit different for the minor diameter. All right, so if we look at that right here, it looks very similar. It's just that this time we're given the pitch within our table, so we don't have to worry about it. Fire department go past here. So let's do an example, right? So if we're given a diameter of 12 metric internal thread, right, then what do? Well, we know we have to go to our table. We said at 12, right? So M for metric 12, we have two options. We can be coarse, we have a pitch of 1.75, or we have a fine one which has a pitch of 1.25. Right, so we start with the first one, with the coarse one, right? Then we know 1.75. We can go back in, we can see that the tap drill in this case would be at 10.3 millimeters. And then we'd have to pull out an equation to find out what the minor diameter is. Right, in this case, will be that nominal diameter D. We know that is 12, right? That's a metric 12. Then this 1.2075 is just the number that we're given, conversion factor. And then we have to use the pitch. Again, this time we don't have to do 1 over because it's already given as the pitch. And that gives us our minor diameter of 9.9. Again, very important that the minor diameter is less than the major diameter, of course. Now that would be for the coarse one. If we go to the fine one, right, we'd have to go in here. We'd have a pitch of 125. Put that in our table. We get our tap drill of 10.5. Put that in our table. And then we can do the same calculation. Now, of course, we just have to change what the pitch is, and we get a slightly smaller minor diameter. Right, so would be what we can see. Now, based on what we see in this table, which of these is the finer thread? And again, the finer thread means that we have more threads stuck close together. Which of these would you say is the finer one? And why? 1.75 pitch or 1.25 pitch? What did pitch mean? What do I measure with a pitch?
I forget the name of the rings per inch.
That's what we use for Unified National. And that's where we say per inch. The pitch really says what the distance is between those two. Right. So if you think about one turnaround, right? So if you start on a crest and you walk all along a crest until you come back up to the same space, right? That distance, the lateral distance that you've moved, that's what we call the pitch, right? If we think about like, those pictures that I had where you have all these, diagonal lines on it, the distance between the tops of each of those, right? That's what we call the pitch. Now, is having a larger or a smaller pitch mean that you're a finer or a coarser screw? Think about it. If I have a small number in my pitch, I'm going to have crests or have threads that look like this. If I have a large number, they're going to look like that. But here one, there one, and so on and so on. Right. So in this case, the smaller this number is, the finer my pitch is going to be. That's something that's a little counterintuitive or a little annoying between the two systems, because remember that the Unified National one had it as threads per inch, right? And that, of course, the bigger the number is, the finer it is. But here's the actual thread distance, so it's the smaller the number, the finer the one. Of course, we could also just remember that we just looked at the table and one said coarse and the other one said fine, so that could have also helped us to understand where we are. All right, so that one is the finer one. So let's do an example just like we did for the Unified National one. So we are supposed to write the thread note for a 10 millimeter fine. All right, so we go into our table, look at 10 millimeters, M10, and we have coarse, but we're looking for fine. So our thread note would just be exactly what we have there. Right, it would be M10 X 1.25. That's our entire thread note, all that we need to know. And again, we're using these thread notes because they're a lot easier than having to draw what the thread actually looks like. And then once we have that, we could write a table again, right? So we have our thread note that we just created. We can get the tap drill diameter from our table, so 8.75. We can find what our minor diameter is through our equation, in this case 8.49, which is less than 10, so it's good. And then we can say here's the pitch is already given to us, so maybe we'll get the threads per millimeter. So we just do 1 over 1.25, right? 1.25 is the pitch, so we get 0.8 per millimeter. All right, any questions? No questions whatsoever. All right, if there are no questions, then I will let you start working on the same set of table as we're doing here. All right, so we have 2 for Unified National, one that's 1/2 fine. They want you to write out what the thread note is, what the major diameter, what the minor diameter is, and then what the pitch is. Now be careful that this, I'm asking for the pitch here, right? The table is going to give you threads per inch, but I want to have the pitch, right? So you have to do 1 over that. That's for 1/2. Then for a number 2 course, right? These all be both Unified National. And then also 2 for metric ones. One is an M8 fine, And here I want you the thread node, the tap drill diameter, and the minor diameter, and then the threads per millimeter. Right, so again, do 1 over, and then the same for an M12, of course. All right, questions about any of that? And I think I will let you start working on it. Should be relatively straightforward. If you finish this quickly or before the time is up, then of course you could also finish off any of the tolerance work that is still out there for those who have not turned it in. I see somebody already, some of you have already turned it in, so that's very good.